Most tech breakthroughs die not because the code is bad or the idea isn't good, but because they crash into a wall of physics. We are told to wait for software optimization when the real bottleneck is often just heat and electricity. This video exposes why promising prototypes stall at the manufacturing layer, the brutal reality that you cannot run infinite power on finite silicon without cooling it down first. Consider the recent hype surrounding next-generation artificial intelligence or electric vehicles, where a prototype hits a wall after months of development. The narrative usually blames algorithmic inefficiency or a lack of user feedback loops. But if we look closer at the transition from active development to final product, the story changes completely. Teams often struggle not with specification errors in their code, but because they encounter physical limits in silicon physics and heat management that no amount of software tuning can fix. The energy required exceeds what current cooling or power distribution can safely handle. This is the fundamental misunderstanding driving so much frustration today. While software teams focus on feature sets, user feedback loops, and product discovery cycles, the underlying hardware has hard ceilings that cannot be coded around. As noted in industry analysis regarding specific arXiv papers submitted back in April of 2019 by researchers including Antti Nutis alongside Victoria Pallison and Giovanni Maccani, the constraints are deeply rooted in the physical layer. The delay is rarely a missing app feature or a buggy line of code. It is often simply that you cannot fit more water into a pipe if the pipe itself has reached its maximum diameter. To understand this physics wall, we must look at power density and thermal dissipation without getting lost in jargon. Imagine trying to pack an entire city's worth of electrical activity onto a chip no larger than your fingernail. That is the challenge engineers face with modern silicon. As you push more transistors closer together or ask them to switch faster, they generate heat at a rate that scales non-linearly. If you double the power consumption in a small area, the temperature does not just rise, it spikes exponentially. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Think of an engine overheating on a hot day. The software inside is perfect, but if the radiator cannot move enough air or liquid to carry away the waste heat, the machine shuts down to prevent destruction. This thermal dissipation problem is why promising prototypes stall at the manufacturing layer. You can write infinite code in simulation, but once you build it, that code must run on physical matter governed by thermodynamics. The feedback loop fallacy suggests we should just listen more carefully to user data or iterate faster. But true innovation often requires engineering teams to push against the boundaries of what is physically possible before users even know they need it. This brings us to a deeper layer of the problem: why some technologies take decades to mature and others stall permanently. This phenomenon is known as captured innovation. Dominant firms sometimes delay disruptive hardware innovations not because they lack the code, but due to a conflict between creating breakthroughs and protecting existing revenue streams. Even when physical solutions exist, market forces may withhold them if they threaten legacy infrastructure or require massive capital shifts in manufacturing capability. Consider the history of Netscape marking the birth of the internet 20 years ago. The software was revolutionary, but it required new networks to support it. Similarly, today's hardware breakthroughs often wait for the physical supply chain and power grids to catch up with theoretical capabilities. Marty Kagan spent 10 years working specifically as a developer at HP Labs before transitioning into product leadership, giving him 35 years of career experience in observing how technology actually moves from concepts to reality. His observation holds true. Relying solely on user feedback can stifle breakthroughs because customers cannot imagine what they need until it exists, and often, that thing requires physical infrastructure we do not yet have. The cost of scaling is dictated by a landscape where economies of scale and government policy dictate success more than raw code does. We see this clearly when contrasting regions or sectors that lead in physical innovation versus those stuck on software-only narratives. Some regions lag behind because they focus only on the application layer, while others lead by focusing on the physical foundation, such as commercial nuclear power generation or battery manufacturing. These are not just markets. They are engineering feats of managing massive energy flows and heat rejection at a global scale. Innovation is often about mastering the supply chain and energy grid rather than just writing better software. When a company announces a breakthrough that sounds impossible, or when a promising prototype stalls for years, look past the press release about features and capabilities. The delay is likely an engineering problem involving power density, how much energy fits in a chip, or thermal dissipation, how to get rid of the heat before it melts everything down. This distinction changes how you evaluate new tech news forever. You no longer need to be an engineer to see that software does not run on air. Every AI headline still depends on something physical: power into a building, heat out of a rack, wafers through a fab schedule. When capacity tightens, the constraint is rarely a missing app feature. Today we followed the engineering bottleneck behind the software story, revealing why the future belongs to those who master the physics, not just the code. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.